Remember, in a previous lesson, we talked about how to describe the motion of an object by keeping track of its center of mass as a function of time. In this lesson, we're going to focus some more on the relationships between displacement, velocity, and acceleration, and I'll go through how to write down mathematical expressions for some of the simplest types of motion. Now, location in space requires 2 or 3 coordinates, which we can study using vectors. But to simplify the maths a bit, we're going to look at the case when location needs just 1 coordinate. Once you're comfortable doing the maths with 1 coordinate, you'll be able to move on to working with more dimensions. And in fact, a single coordinate is enough to keep track of speed along a fixed path, such as a car on the highway, a train on its tracks, or an airplane on a straight flight path. So to describe where a train is along a track, we just have to write down where the center of mass is at each point of time, x as a function of t. There are a few decisions to make first. We must decide where the 0 point along the track is, and maybe also what will be the 0 point in time. And then we have to decide which direction along the track is going to be positive. It doesn't matter too much how you choose these things, you just have to be consistent for the whole time you're working on a particular problem. Imagine I record the position of my train as a function of time, and when I plot this information it looks like a straight line. Let's suppose the time axis tick marks are 1 second each, and the x-axis tick marks are 10 meters. Then we can calculate how fast the train is going as delta x over delta t, and for example we get 6 meters per second. I can choose a longer time interval, say 3 seconds, and see that the displacement is 18 meters, so the velocity is still 6 meters per second. In fact, any time interval I choose will give me velocity equals 6 meters per second. The velocity is constant, and a graph of the velocity as a function of time is just a horizontal line. Now if we think about acceleration, there's no change in velocity, and so the acceleration is 0. Now let's look at a graph of x that is not a straight line. We see from this graph that the train travels 10 kilometers in a 10-minute interval, and we can calculate the average velocity for this trip as 60 kilometers per hour. This is the slope of the line that joins the point at x for time equals 0 to x at time equals 10 minutes. If the train had had a constant velocity for those 10 minutes, the x of t curve would look like that red line. Now what further information does the blue curve tell us? If we take a much smaller time interval at the beginning here, there is no change in position, so the velocity is 0. And if we do the same at a later time, we see a steeper slope. These slopes, calculated for very small time intervals, are called the instantaneous velocities. The lines that just touch the curve here are called tangents to the curve, and this is something you'll study more in calculus. From looking at this blue curve of position as a function of time and the instantaneous velocities it implies, it seems the train slowed down and stopped at a station briefly before increasing its speed as it continued on its journey. The velocity curve is drawn in green, and just as slopes on the displacement graph gave us velocity, slopes on the velocity graph give us acceleration. So for this example, we see that the acceleration is negative up until t1, then both velocity and acceleration are 0 until time 2, when the train starts moving again and its acceleration is positive. Suppose now that I'm recording my instantaneous velocity as a function of time, rather than my location in space. If I'm in a car, that means I'm recording data from my speedometer rather than from my odometer. Now how do I figure out how far I've travelled from the velocity information? If the car maintains a constant velocity, the graph of v as a function of time is just a horizontal line, and the distance travelled is simply v times the time interval. This is equivalent to the area under the graph, and the area under the graph trick works no matter how the velocity changes. Let's look at a little example. Suppose a train travels for 60 seconds at 10 meters per second, and then 120 seconds at 20 meters per second. So it will travel 600 meters in the first segment and 2,400 meters in the second. The total displacement is 3 kilometers overall in the total time of 180 seconds. We can calculate the average velocity for the journey as 3,000 meters over 180 seconds. Note the average speed is not 10 plus 20 over 2,
because the time spent at each speed is different. Now what if the car or train accelerates at a constant rate? This means the graph of v as a function of time is just a straight line. And we can figure out some really nice formulas for quantifying how displacement and velocity change with time. First of all, let's figure out how the velocity changes with time. We'll call the starting velocity u. Now, since the acceleration a is constant, the change in velocity over any time interval is just a times delta t, and we find that v equals u plus at. That's the equation of the straight line with slope equal to a and a vertical intercept of u. Now what about the displacement? We know delta x is the area under the velocity curve, so we can break up that region into a rectangle with height u and width t, which has area u times t, and then a right-angled triangle with height v minus u and width t. So that has area 1/2 t times v minus u. After some algebra, we get that x of t is ut plus half at squared. We can also combine these two equations to eliminate time. Let's rearrange the first one to find t equals v minus u over a. And then we can use this expression in the second equation to find a new one. Again, after some algebra, we get v squared minus u squared is equal to 2a times x. Now, when do we actually have constant acceleration? Cars and trains and planes have approximately constant acceleration for short periods of time. And an even more important example is near the Earth's surface, where gravity acts in such a way as to cause constant acceleration to most falling objects, especially when we can ignore effects from the air. This is discussed in some of the other lessons.